Welcome back to ECE 442-542. I am appending notes quite regularly to what we did in class, meaning you might want to look occasionally, and now I've forgotten what I talked about last time, but I think it pertained to, well, I can tell myself what it pertained to if I could find it. Yes, it pertained to the relationship between S and Z. Here you'll see that I have about as much after class as I had during class in terms of notes. Obviously I didn't record another video, but I made some observations in the last lecture. And so if you see in D2L something that says with after class notes, you know that there's something additional added to the lecture material that might be helpful going forward. And in last time we ended on what's the relationship between S and Z, these two complex numbers. Z was equal to e to the st. I now just illustrate that with some observations, or make some observations with that particular relationship. If you're an online student, you only need to do one or the other. You don't need to do both. You either decide you're going to take your exams using Examity, or if you can secure an outside proctor, then you can take your exams using a proctor. Homework 1 is due today. Hopefully everybody's aware of that, and that's not coming as a surprise. We're now in the textbook into Chapter 2, and the first few sections of that will be dealing with difference equations and the Z-transform. Question?
Yeah, for the homework, for the MATLAB portion, is it okay we turn it as a .m or .mly?
So the question is, can we turn the MATLAB material in as a .m? I would say it's more convenient for the grader to just have one PDF file to open up. So if you could copy the .m file into a Word document, for example, and save that as a PDF with the Word document containing copied and pasted figures, then the grader only has to open up one file from each student and not 20 different files. And if the M file, in this case, the M file might contain most of the information needed to produce these plots or figures, then maybe all you need is the M file. But subsequently, in future MATLAB, it might be important to know what's the result of this executed statement. That result needs to be included, and so if you did a diary file with an echo on, then you could simply plot the capture the diary file, and that would show you the MATLAB commands and the output that was generated. Obviously, if you said y is equal to step of something, I don't want to see 1,000 values of y. That's what the plot is for. So save paper or save pages of a PDF document and suppress that kind of an output. But if I said, what are the eigenvalues, then you might want to show those and not semicolon EIG of A, for example. Essentially, if in 6 months you looked at what you're submitting and you couldn't make heads or tails of what you were doing, that's not enough material in your submission for the MATLAB assignment. If you can look at what you've submitted in this PDF file pertaining to your MATLAB, and it makes sense, oh, these commands, oh, that produces this transfer function, oh, it produces this plot, this result, oh, and I've actually said what that plot is showing me. I forgot what we were trying to produce. Oh, this was the settling time. Well, if you write some of those notes down, I think it will help you in 6 months to refer to that document instead of just saying, I don't know, I've forgotten what MATLAB commands correspond to. I don't know what we were trying to do. That's what I'm trying to get you to document in your MATLAB submission. Question?
So the way you wrote like notes and then the information under the graph, we should do that when we submit this MATLAB.
The question pertained to my example, I believe, of MATLAB, where I believe I included some comments. Maybe, I don't know how silly some of the comments were. If the comments were, oh, plot the, maybe that's not necessary if it's a plot statement. But if it was something that you know you may not remember what that function is doing, or you might say, oh, I'm actually now going to compare the eigenvalues, you might state that as your comment in your MATLAB commands. But it's sort of like a programming class if you say, okay, make the comments meaningful so that it helps you understand what you were doing and why you were doing it. Yes?
For people that already submitted it in the past, can we just follow these instructions for the next?
So if you've already submitted, I want you to go home and spend the next 10 hours trying to make sure it's like I talked. No, it's okay this time, but next time, for the benefit of the grader, I think, and for you, if you were very terse in what you submitted, try to make everything more like what I've tried to explain today going forward. Going forward, homework 2 is not due next Monday. I've given you a couple more days. It's due on a Wednesday. And then following that Wednesday is our exam. Our exam is on the 19th, and what I'm wondering is, would you like to have an exam review session at 7 o'clock after our normal lecture a week before the exam? So I need to check to make sure this room is available. It has been so far, but maybe I need to verify that. I don't want to say, okay, let's have our review session, and in comes 100 students for some other event. So let's verify that, but it sounds like people are interested in a review session for exam number 1. What I want to do now is, today, is talk about really what we were leading up to last time. We were talking about the relationship of this operator z. Can we now use that to go from time domain to difference, or to frequency domain? Question. So I will try to produce homework solutions for the different documents. I can't guarantee that they will be graded before the exam, but I think you should be able to compare your work with the solutions. And can you access your work even after you've submitted it on D2L? So you can go in, even if you've somehow, if the dog ate it after you've submitted it, now at least you have it in a repository in D2L. You can now see that and compare it with the solutions that will be provided. We'll first look at how do we go from a difference equation time domain into a transfer function, and then we'll start doing the z-transform, trying to figure out how do we convert a waveform in the time domain into its frequency domain representation. Very similar to how you can Laplace transform waveforms. It's just now we will actually make sort of something out of our region of convergence, because just if somebody says you took a digital controls class and you don't know anything about the region of convergence, or causal and anti-causal, or two-sided sequences, you don't know that, I want you to be a little bit aware, and on the exams obviously demonstrate your knowledge and understanding of those concepts. Whereas in Laplace, a lot of times we were simply assuming our waveforms were one-sided. They were only valid for t equals 0 up to infinity. Now we may have waveforms that are defined for n from minus infinity up to 0, or from 0 to plus infinity, or from minus infinity to plus infinity. We want to understand, how does that influence our region of convergence? And I'm going to say this and say this and say this, but the region of convergence is not the same as the domain of stability. Or if your waveform is bounded or unbounded, does not mean the same thing as having a bounded or unbounded region of convergence. Those are two different things. Hopefully that will all become second nature as we go through and learn this. Now, I have produced a template, so I'm going to be going through this maybe a little quicker than what you can write it down, but I'm hoping you now have access to the template of commands. But now, from before, we know z to the minus 1 in the frequency domain corresponds to a delay of 1 sample period. That's how we will use z to the minus 1. If we now say, oh, here's a signal that's been delayed, so here we want a transfer function, and that means we're going to neglect initial conditions. We want to go from time domain to frequency domain. Here's what we're doing. If I say script z of curly brackets, a waveform y of n, and in this case it's y of n times u of n is really just a switch. U of n is only 1 for values of n non-negative. 0, 1, 2. That's the only time u of n is on, and it has a value of 1. Z of y of n u of n says, oh, I'm only z transforming the y's for n equals 0, n equal 1, n equal 2, etc. That we will then say is capital Y of z in this case. Now, what happens when we look at the z transform of y of n minus 1 and u of n minus 1? Well, we just said a delay of 1 in the frequency domain corresponds to z to the minus 1. And what's in the curly brackets? That's really just a 1 period delayed version of y. So it seems to make sense that that should correspond to a scaled version of capital Y of z, and the scaling factor is z to the minus 1. A lot of times we don't write that sample period explicitly in the argument of our time domain waveform. In fact, it's y of little n capital T or little n minus 1 capital T, but a lot of times for simplicity we simply neglect or assume or imply that that capital T is present, and so we don't even write it. Is it clear, the notation? So now to find a transfer function, we're going to neglect initial conditions. We want to know these signals are now happening for positive values of time. What's the transfer function between an input and an output? And here's a point that maybe won't make a lot of sense now, but it will when you're starting to take z transform. Is there a difference between y of n minus 1 turned on at n minus 1 or y of n minus 1 turned on at u of n? And let's just try to get a feel for the difference between these. There is a difference, and here's the thinking. Here's a y of n, and in this case it's a finite sequence. It's a mess, but I was trying to make it such that if I shifted it in time, all the values didn't look the same. So now if you shift this, it's going to be clear which value of y is corresponding to what value of n or index in the sequence little n. So don't worry so much about that. Let's look at it in table form. Here is y at time n for the different values of n. I'm stopping it at minus 5 and plus 5. It's no longer has a non-zero value. Y of n is just non-zero between minus 4 and 4 in our time index little n. If that's y of n, what's y of n u of n? This is really illustrating what U of n is doing.
Y of n, U of n is just Y of n for anything greater than, for 0 and anything.
Yes, so Y of n, U of n is going to be an exact copy of this first row on the right-hand side. Everything with negative indices is going to be zeroed out. Meaning, Y of n, U of n is going to be 0, 0, 0, 0, 0. For all those values of n, U of n is 0. So U of n times Y of n gives you nothing. You have 0 times something, you're going to get nothing. But at time 0, U of n now becomes 1. So now Y of n becomes 1, 1 half, 3 halves, minus 1, 2, and 0. What's Y of n minus 1? Now just plug in to Y of n minus 1 and figure out what that corresponds to. For n equal to minus 5, it's Y of minus 6. What's Y of minus 6? We agreed that it was nothing up to and including n equal minus 5. That's now 0. When n is equal to minus 4, Y of minus 4 minus 1 is Y of minus 5. Oh, that's also 0. When n is equal to minus 3, we're really asking what is Y of minus 4? Well, that was minus 3 halves. And do you see that I'm now really just shifting all of these by 1 unit of time, little n, and I can now start to write this down rather quickly and make sure I don't make a mistake. And maybe we could put in a 6 out here, and I didn't even have to cut and paste my page width, as long as I made my table kind of narrow. This I said was 0 by definition. This was 0, and now this one is 0 because of that. Now, what is Y of n, U of n minus 1?
0 to -1.
So now what I do, just if it's not quite clear, I say, okay, what value of n in this U of n minus 1, when will that argument of U of n minus 1 be 0 and 1, 2, 3, or non-negative? So I say n minus 1 greater than or equal to 0. N is now greater than or equal to 1. So this turns on for n equal to 1. Is that clear? So U of n minus 1, I just copy those down for all values of n beyond 1. So now I could say, oh, this is going to be 1, 1 half, 3 halves, minus 1, 2, and 0. And that, this is going to get kind of messy, but that's now this and that. And so now I've just shifted Y of n, I've delayed Y of n 1 time interval. And so now if I z transformed Y of n, U of n, I would get capital Y of z. Do you see I would get exactly the same sequence in the time domain? I've just shifted it 1 unit of time if I z transform Y of n minus 1, U of n minus 1. Now let's compare that to this one. What value of n does this Y of n minus 1 get turned on? This turns on at 0. So now I'm saying, oh, I have that. I have this, 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 and this. And I hope you see that I now have an extra term. Which in a sense would be an initial condition term in our Z transform. But I'm going to neglect initial conditions for this first discussion involving going from difference equation to the frequency domain or the transfer function. I hope you see, though, that now there is a difference between y of n minus 1 u of n minus 1 and y of n minus 1 times u of n. So after our thinking, here's your 2-penny answer. After our thinking, is y of n minus 1 u of n minus 1 the same as y of n minus 1 u of n? Hopefully you realize that that's a no. And we can verify this later, that in fact if we Z transformed y of n minus 1 u of n, we would obtain what we thought, Z inverse capital Y of Z, but we would also have this extra piece hanging on that value or that expression, and that would be our initial condition. Very similar to how you had initial conditions when you took the derivative of a signal in the Laplace domain. You had to subtract off these initial conditions. Here we have some initial conditions remaining. What we want to do now is use this process or this thinking to actually convert from time domain linear difference equation into the Z domain and obtain a transfer function. And when we're talking transfer functions, it means we are not interested in initial conditions. If that's the case, how do I now take this or Z transform this linear difference equation? And it's time invariant. I'm assuming these A's and B's are not functions of n. So A1, A sub 2, A sub 3, those are just constants. B1, B sub 0, B sub 1 is a constant. If I Z transform little y of n, what's the Z transform of little y of n? That's pretty easy. That just comes straight through as capital Y of Z. What's the Z transform of that delayed one time step in the time domain? You get the drill. Now we can say, oh, that's the next term is A sub 2, Z to the minus 2, capital Y of Z, plus A sub 3, Z to the minus 3, Y of Z, equaling B sub 0, capital X of Z, plus B1, Z to the minus 1, capital X of Z. We have some common terms in that transformed expression, capital Y of Z and X of Z to be specific. Let's factor those out, and we now have 1 plus A1 Z to the minus 1 plus A sub 2 Z to the minus 2 plus A sub 3 Z to the minus 3 times Y of Z is equal to B sub 0 plus B1 Z to the minus 1 X of Z, where this Y of Z is our output and X of Z in this case is our input. And I hope you can see now that we can solve for, we can divide both sides by capital X of Z. We can divide both sides by the coefficient or the polynomial scaling capital Y of z, and now we have this transfer function. The transfer function capital Y of z over x of z. And what do we, if I said, oh, this transfer function is between what signal and the other signal? Well, I've labeled it up above as input and output. The input's in the denominator, that's capital X of z, and the output is capital Y of z. So that if you now filtered or used this transfer function to filter a signal, you would produce an output. And a lot of times we may write it in terms of positive powers of z. How did that happen? Or how can you demonstrate this?
Multiply it by z to the negative 3 over z to the negative 3.
Almost. We need to multiply it by 1, don't we?
Or z to the 3 over.
So now we need to multiply it by z to the 3 over z to the 3. We look at the highest z to the minus 3 in this case, and then we just do what we need to make that 1. So now we multiply that by z cubed over z cubed to get or obtain a transfer function in terms of positive powers of z. How would you assess if this particular transfer function was stable? Would you look at your B's, your A's? You're always wanting A's, aren't you? So now you look at the roots of the denominator polynomial, and that, what do you want where do you want those roots? Inside the unit circle. And then if I injected a bounded waveform into that transfer function, I would produce a bounded output, because my poles, or the roots of the denominator polynomial, are inside the unit circle. Now we've already used the operator, so now you can immediately, this z, or z to the minus 1, you can now immediately take a time domain difference equation into a frequency domain transfer function. Let's now look at how we might z-transform sequences of numbers. How do we take a waveform, values of numbers in the time domain, and produce a z-transform? And to think about that, or to get us thinking about what we've already done or know, we can remind ourselves about the Laplace transform. And here I'm using the one-sided Laplace transform, where I'm only interested in time from 0 to infinity. And depending on what you're looking at, maybe somebody might say, oh, you're scaling or weighting the waveform in the time domain by a kernel, e to the minus st, and now you're essentially weighting this over all frequencies, s, and you're integrating time out. You're saying for all time, let's scale x of t by e to the minus st and see what happens with our frequency content in that signal x of t. And that now produces this capital X of s. Last time we said, oh, we know the relationship between s and z. We tried to convince ourselves that z was equal to e to the st. Here you can kind of see how you can use that now. If you sample this argument in your Laplace transform for certain instances of time, little n, capital T. If we now substitute little t, or replace little t with little n, capital T, we now end up with our kernel, or our weighting, being this e to the minus snt, or knowing what we know about exponents, we can sort of move those around and say, oh, I have e to the st raised to a minus n power. And we know what e to the st is. That's z. Now we are going to be weighting our sequence in the time domain with this operator, z to the minus n. Just like we weighted our time sequence in the continuous time setting with e to the minus s little t. And we can define different z transform expressions. We could say, oh, I'm interested in the one-sided, when x of n only is going to assume values, non-zero values for my time index n from n equals 0 to infinity. What's that z transform? Or you could say, you know what? My sequence is valid or known from minus infinity to plus infinity. So what is x of n? We've been saved by the bell. I was going to ring that in a minute, but the previous instructor grabbed it off the desk. So if you're listening to this, you're wondering, what is he talking about? And I should have rung it before he took it. I didn't know why he was walking in the room. I should be closer to my podium. There was a bell. Maybe you all should have bells on your desk, and if I go chasing rabbits, you just hit that bell and say, let's get back on track. Okay? Yeah, I have that in my meetings sometimes. We have an imaginary bell, and they just start doing this, and I know what they mean. Let's get back on topic. So here is now our one-sided and two-sided. I think it's clear the difference. In one case, we're summing from n equals 0 to infinity. The other one, x of n, we want to be summed, or this expression defined for n equal to minus infinity all the way up to plus infinity. Let's now see how that works. What's the z transform of some common time domain waveforms? The unit pulse. And some books, and I might say the unit impulse. This is now the Kronecker delta. I had a student go, what kind of an impulse are we dealing with here? It's not the Dirac delta, which has an infinite amplitude and an area underneath it of 1. That's the one you've used in the Laplace where you were sifting things or wanting to know, oh, I want to actually excite my system and initialize all the energy storage devices. You might excite it with an impulse. That's the Dirac delta. We can excite a system now in discrete time with something that's maybe more understandable. That's the pulse that has a value of 1 at time n equals 0. That's delta, or x sub a of n, or I might write it as delta sub a of n if I want to call attention to the fact that that signal is a delta signal. And it looks like what I've tried to draw here for little x sub a of n. It's 0 everywhere except for n equal to 0. And at n equal to 0, it has a value of 1. Do you see how I could change that if I said, oh, I want a pulse at n equal 2? Now that would be delta sub a of, the argument of that would be n minus 2. We would want the argument to be 0 at the value of n where we want that pulse to occur or exist. And so we would set our argument to 0 and we would say, oh, we want that will be 0 at n equal to 2. Here, let's just look at it at the origin, or at n equal to 0. Let's find the z transform. Here's our definition. Capital X sub a of z is now this sum of our waveform, x sub a of n, scaled by this complex number z to the minus n. What does that look like? Well, let's write that down. We have, I don't want it to be in red. I now have x sub a. Do we see that for little n equal to negative values, it's 0? We're scaling z by 0. Let's just look at the positive side. It doesn't matter. We could also, well, I could have done it the other way, but let's say there. That's n equals 0. We also could say, oh, what is it at n equal to 1? I guess what I was saying to convince you is to say, oh, dot, 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 plus x sub a of minus 1, z to the minus minus 1 plus x sub a of 2, z to the minus 2, dot, dot, dot. In general, we have to keep track of all of these terms, and what we really want is capital X sub a of z to give us a valid expression, a bounded expression, in order for it to really exist or to be well behaved. I'll use different terms to describe this. What is little x sub a at minus 1? From this picture, I hope it's clear that that's 0. What's x sub a at time 0? That's 1. All of these others are 0. What do we have left? Or what is z to the minus 0? What's 1 over z to the 0? 1. Z to the 0 is 1. So now all of that is 1 times 1, or that's 1. The z transform then of the unit pulse is constant. It has, as far as z is concerned, z is a frequency. As far as this pulse, it essentially has equal frequency weighting for all frequencies. That's why if you excite something with that unit pulse, you're exciting all the frequencies with the same weight or scaling value. Waveform B is going to be the unit step in discrete time, but let's just remind ourselves of what that looks like in the continuous time setting. Here is our aside. Hopefully you remember, what's the Laplace transform of a unit step? 1 over s. And if you now wanted to see the pole 0 diagram of 1 over s, you would say, what finite values of s cause that to vanish? There are no finite values of s that cause, so there are no zeros. There are finite values of s that cause the denominator to go to 0, which would make the whole thing go unbounded, and that's where we get the x. That's at s equal to 0. We now have a pole at the origin in the s-plane. That's in the frequency domain, and our time domain waveform is constant for all non-negative values of time. Okay, that's now in your mind. Let's now move on to waveform B, which is the unit step in discrete time. Now we're only worried about this signal at the sample periods, or at these time indices 0, 1, 2, 3. We're not saying anything about what's happening in between. But we now have a unit step. If I said, what's this sequence? You would say 1, 1, 1, 1, starting at n equals 0. Or you could write that in sort of notational form. You say 1 for n greater than or equal to 0, and it's 0 otherwise. Now, let's find the z transform of that. What do I want the lower index to be? Or what is x sub b of n? It's usually 1, but now I need to make sure that I don't pick up values of time index n when it's not equal to 1. So what is the lower bound on little n in this summation? 0. And I now scale that by z to the minus n. Or that now becomes, for n equal to 0, I have 1 times z to the 0 plus 1 times z to the minus 1 plus z to the minus 2 plus z to the minus 3, and that just keeps going. And this is, you've probably seen before, but this is now an infinite series. I actually want to be able to write this down in a more compact way, or to find a closed form expression for that, and I really want this capital X sub b of z to be well defined. And for that to happen, I need that sum, or for it to be well behaved, I need that sum to give me a finite value for any value of z, or for my specific values of z that I evaluate it for. Okay? So now let's look at finding this closed form expression for x sub b of z. And we did this in our example when we were talking about our bank account, didn't we? How could I make a similar looking expression, maybe that might differ by one term in that sum? How could I now modify x sub b of z to make it look almost the same, but maybe just a little different? What's the strategy? Christian? Pardon?
Is it just to, I guess, multiply by a factor in both sides?
So what's my common ratio in the terms when I go from one term to the other? This is kind of what you're looking for. What's the difference between each of the terms? What's my common ratio? Z, 1 over z, or z to the minus 1. Each term differs from its neighbor by z to the minus 1, or this common ratio. What if I now used that to scale the entire thing? Or what if I weight, not W-A-I-T, but W-E-I-G-H-T, what if I weight capital X sub b of z by z to the minus 1? Now I've scaled 1 by z to the minus 1, and I'm just going to write it underneath that one. And I now have and what I will refer to as the tail of this sequence, it now looks the same. And I now can compare these two expressions. And by compare, I'm meaning subtract one from the other. If I subtract the bottom one from the top one, I now have 1 minus z to the minus 1 times capital x sub b of z equaling, and what's left? The only thing that differs is the 1 in the top expression. So now I want to know, when is this valid, or what am I assuming is true for this to be a valid expression, capital X sub b of z. By well-behaved, I mean it's bounded. I don't want my right-hand side to go to infinity, then it doesn't make any sense. I can't really compare or say, oh, here's infinity, and I'm subtracting infinity and infinity. Well, that's not a valid thing to do. When is this going to be valid or well-behaved? I'm going to say it's well-behaved or the sum converges and maybe an easier way to think of that would be, oh, let me just write this in that way. Now I'm adding something that I'm simply increasing the power of, and if I keep squaring or cubing or raising it to a higher and higher power, when is that tail going to sort of disappear so that the sum is well behaved? So if I want that tail to eventually just add up to a finite number, I need that parenthetical common ratio to be less than 1, don't I? I need z to the minus 1 to be less than 1. Then if I raise it to higher and higher powers, that starts collapsing. So for this to be well behaved, or for that sum to converge to a finite value, so let me say sum converges to a finite numerical value, that's going to happen when z to the minus 1 is less than 1. And this was the common ratio. Or I could now solve that for capital X sub b of z and say that I have 1 over 1 minus z to the minus 1, and that converges. That's this piece. I know that's going to be this expression as long as z to the minus 1 is less than 1. But that's kind of hard to maybe think about z to the minus 1 less than 1. Well, that's the same as 1 over z less than 1. Or we now know that the magnitude of z needs to be bigger than 1. And how else could we write that expression for x sub b of z? We could write it in terms of positive powers of z. Multiply both top and bottom by z, and I now have another form for the z transform. What were we z transforming? 1, 1, 1, right? The unit step. This is now z over z minus 1, and that's true, or it makes sense, or it's valid when z is bigger than 1. And that closed form expression, which is right here, is going to allow me to say, oh, and we call that region where the series is well behaved or bounded is our values of z that cause that sequence to be well behaved is our region of convergence. Those are the values of z where we have well behaved or a sequence that is bounded. And we now shade that in the z-plane. Maybe I should let you draw that if you don't have it already. We now have our complex z-plane. What finite values of z cause that to vanish, that transformed expression? Do we have any that cause it to vanish? By vanish, I mean make it go to 0. When will capital X sub b of z equal 0 for a finite value of z? Can I plug in z equal to 0? The denominator's fine. It's minus 1. The numerator is 0. This has a 0. Capital X sub b of z has a 0 at z equal to 0. That's what the open circle corresponds to in this z-plane plot. What value causes the denominator to go to 0 or the whole thing to go crazy or unbounded? That's, we set z minus 1 equal to 0. That's when z is equal to 1. That's the pole. We now have poles and zeros of that transformed expression. The 0 is at the origin. The pole is at 1. What's the region of convergence? That's what I'm shading. That's all values of z outside of z equal to 1. The region of convergence is, and here you'll hear me say this sometimes, and this might be confusing, the region of convergence is unbounded. It goes all the way to infinity. Doesn't it? Because we needed, for this expression to be valid or to be well behaved, we needed z, the magnitude of z, to be bigger than 1. That means we just look at the complex z-plane and we say any value of z that has a magnitude bigger than 1, and that could go all the way off to infinity. Then this sequence has a well-behaved z-transform of z over z minus 1 for all values of z outside this circle of radius 1. And a point in that region of convergence could be infinite. So you have an unbounded region of convergence. You have the entire z-plane except for this missing disk, the disk being, in this case, the unit circle. Let's look at a little bit more interesting waveform, the exponential waveform. Here I'm showing the analog version. Red is when A is positive, and black is when A is negative. When you have e to the 2t, that's going to go unbounded. That grows exponentially. If you had e to the minus 3t, that now is decaying. And the difference between those is the sign, S-I-G-N, of little a. And what's the what's the Laplace transform of e to the at? I'm sure you can't even tell me since it's right there on the screen. It's 1 over s minus a. And that depends on the sign of a. If a is negative, if you had, what's the Laplace transform of e to the minus 3t? Oh, that's 1 over s plus 3. You should remember that from earlier courses. Do I have any zeros in that transform expression? 1 over s minus a. Do I have any finite zeros? Do you see you actually have an infinite zero? You have a zero at infinity. If you let s go off to infinity, that expression would vanish. So if somebody says, oh, what are your zeros at infinity, then they're really asking you what values of s cause that to vanish. And in fact, if you let s go to infinity, you do have a zero at infinity. Typically, we just worry about finite values of poles and zeros. We have no finite zeros, and we have one finite pole at s equal to a. If we said, oh, a is equal to 2, we now have e to the 2t. Can you find the Laplace transform of that? That's 1 over s minus 2. Yes, you can. Where's the pole? 2. If that corresponded to, instead of a waveform, if that was the impulse response of a system, if it now, when you hit the system with an impulse, it gave you an e to the 2t, that would be an unbounded response due to an impulse. That's now an unstable system, or an unbounded waveform if you were dealing with its waveform. Let's now look at the discrete version of the exponential waveform. That's now where we have r raised to the n. This gives us exponential behavior. And you can see what capital R, maybe to get some insight into why is it a capital R. Well, look at what happens when we sample e to the at. If we sample e to the at, we're replacing little t with little n capital T. And we're left with an ant, e to the ant. What do you think of when you think of an ant? How fast does it move? Well, I guess it could scurry pretty fast in its scale, but to us that may seem kind of slow to get a mile. So e to the ant, that gives you a time. That's kind of this time behavior, and that's really what this exponential is telling us, our speed of the response. And if we play with the exponents, we have e to the at raised to the n. That e to the at is our capital R. That's r to the n. And you can look at different versions of that. You have x sub c of n with r less than 1. We have the exponential decay. Pick a favorite value for r, capital R, maybe 1/2. So now you have 1/2, 1/4, 1/8, etc. That's exponentially decaying. The other side of that would be with r bigger than 1. R is now 3. Now 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 27. That's exponentially growing. What's the region of convergence of that waveform? Well, let's see if we can figure that out by doing similar analysis that we just performed. Let's find the z transform of this exponential. And let's just make it right-sided, meaning let's let let's let x sub c of n be defined for n equal to 0, n equal to 1. That's the right side of this origin in the time sequence. what do we have when we sum that? Well, now we have x sub c of 0, z to the minus 0, plus x sub c of 1, z to the minus 1, plus x sub c of 2, z to the minus 2, etc. And that may not help us too much, but now let's look at what those x sub c's look like. What's x sub c of 0? That's 1, and z to the 0 is 1, so let's just write that as 1, plus r to the 1, z to the minus 1, plus r squared, z to the minus 2, etc. Do you know now what I'm wanting to do? I want to see, can I now find the region of z that allows this sequence or this sum of infinite terms to be well behaved? Let me first write this in a form that I can identify the common ratio. Or I can now say, oh, that's 1 plus r z to the minus 1 to the 1 plus r z to the minus 1 squared When is that going to converge? That sum. I'm having some factor and I'm raising it to higher and higher powers. What?
Z is less than RZ.
I just look at that parenthetical expression and say, there's my common ratio. I just need that to be less than 1. And use that to figure out what's going to happen. This is going to now converge when r z to the minus 1, the magnitude of that is less than 1. I'm going to have a well-behaved sum. Or I now can say, okay, x sub c of z is 1 plus r z to the minus 1 plus r z to the minus 1 squared or I can do my strategy that I've been doing all along. I can scale that by the common ratio. The tail looks the same. Comparing those, or subtracting the bottom from the top, I can now write that as 1 over 1 minus rz to the minus 1. Or what's another way of writing that in terms of positive powers of z? Multiply by 1, where 1 is z over z. I now have z upstairs and z minus r downstairs. And for what values of z is this z transform defined? What's the region of convergence? I now need this common ratio, its magnitude, to be less than 1. Or or I now need the magnitude of z to be outside of R. And where are my poles and zeros in this expression?
0 at z equals 0.
I have a 0 at z equal to 0. That's the open circle. And my pole is when the denominator is 0. That's when z minus r is equal to 0, or when z is equal to r. And my region of convergence is defined as long as z's magnitude is outside this disk of radius capital R. That's my region of convergence.
It needs to be outside.
Pardon?
It needs to be outside the inner circle, right?
So now, where is capital R relative to the unit circle? Did I define R as I was formulating this Z transform? Did I actually specify what capital R was? Here. Did I define R? In that expression, do you see a value for R or a... Does it have to be greater than 1? Does it have to be less than 1? Did I say?
I thought R was
What is R? R is e to the at. Did I find little a? That's just to connect it with a time domain exponential. I just left R unspecified, didn't I? But what did I find in this process? I found my region of convergence, the values of z that cause that sum to be well behaved. That is for values of z outside of capital R. But capital R could be 1/2. Then what's the time sequence behavior if capital R is 1/2? What's the waveform doing as a function of time?
decreasing.
It's an exponential decay. What if capital R is 3?
It's
It's
an increase in exponential.
an exponential increase. Can I still find the Z transform?
Yeah.
Yes. Could I find the Laplace transform of e to the 2t? Yes. That was 1 over s minus 2. So you can find the Z transform of an unbounded waveform. You just have to know what's my region of convergence. What values of Z cause this sequence to have a bounded sum? This picture then didn't depend on the value of R. This picture is consistent whether R is 1/2 or R is 3. What you're going to learn, though, is you can determine the sequences in the time domain nature, whether it's bounded or unbounded, relative to where this region of convergence is relative to the unit circle. Suppose I put the unit circle in this picture. Suppose that's the unit circle. This is now 1 minus 1 j minus j. What can you tell me about the time domain waveform little x sub c of n when R is such that you have this picture in the region of convergence? It goes unbounded, doesn't it? The time domain waveform. Where is the unit circle relative to the region of convergence? Is the unit circle contained within, well, does it lie on top of the region of convergence, the unit circle? No. The unit circle does not contain that phrasing might be a little confusing because you're saying, well, it's around it, it's bounding it. But do you see what I'm trying to indicate? You can have a waveform in the time domain. You can have its Z transform. You can now determine its behavior if you now look at how that R is related to the unit circle. What if my unit circle was in fact here? If that's now my unit circle, do you see capital R is inside the unit circle? R is now 3/4. 3/4, 3/4 squared, 3/4 cubed. That's a exponentially decaying waveform. And where is the unit circle relative to my region of convergence? It's now contained within the region of convergence. Stability does sort of depend on the bounded behavior of your waveform depends on the relationship between your region of convergence and the unit circle. But here, remember that we found that region of convergence independent of whether R was less than 1 or bigger than 1. The time response behavior is unbounded if R is bigger than 1, and it's bounded when R is less than 1, and that now gives rise to what I was highlighting with the unit circle relative to the region of convergence. If the unit circle was contained or lied on the region of convergence, you had a bounded waveform. But if that unit circle was outside of the region of convergence, then you had an unbounded waveform. The relationship between the bounded nature of the signal was influenced by the region of convergence relative to the unit circle. Questions on that? Yes. Pardon? What about R equal to 1? What happens to R equal 1? That's the sweet spot, isn't it? When capital R is equal to 1, that is on the stability boundary. When capital R is equal to 1, now I could actually give you a bounded sequence in time as an input, and if your system had a pole at z equal to 1, your output would go unbounded. I could give you a bounded input that would produce an unbounded output. So that would not be a bounded input, bounded output stable system for R equal to 1. Or what I'm going to give you after this lecture is a little bit more complicated waveform. I'm going to not give you an exponential. I'm going to give you one that's a little fancier. I'm going to give you an exponentially damped or an exponentially growing sinusoid. Where are the poles of that? Well, depending on what R is, they might be outside the unit circle or inside, but they're now off the real axis. They now have an imaginary component. They have some shaking going on. So now the next step, which I'll give you, this is a supplementary piece of material. I'll derive the Z transform of an exponentially weighted sinusoid to see what that Z transform looks like. And you might be thinking, what did the Laplace transform of an exponential sinusoid, an exponentially damped or an exponentially growing sinusoid look like? Think about that relative to what we'll see in the z domain. We'll pick up after that next time.